Hi, I'm Nisan Jian from Arm. Today I will talk about bringing Armv8 Scalable Vector Extension into OpenJDK. Since Scalable Vector Extension is relatively new, so I will take some time to have a brief introduction to SVE, and then I will talk about the JP338 Vector API, and finally, I will talk about the SVE implementation status in OpenJDK and our future work. So this is the SVE overview. Scalable Vector Extension is a next generation of SIMD to Armv8. It has the following main features. First of all, the scalable vector length, which is an implementation defined multiple of 128 bits up to 2048 bits. And another very important feature is the per-line prediction and predicate-driven loop control and management. And it has also some other fancy features like gather load and scatter store, and also the horizontal operations. Please note that SVE is not an extension of SIMD. It is a separate architecture extension with a new set of A64 instruction encoding, and its focus is the HPC scientific workload. So this is the scalable vector. In SVE, it defines 32 new scalable vector registers, Z0 to Z31, and the length of the vector register is implementation defined from 128 to 2048 bits. The bottom 128 bits are shared with ARC64, SIMD, and FP registers. The VLA, the vector length agnostic code generation style, makes the code portable across all possible vector lengths. No need to recompile, which means that one binary can run all implementations of SVE, so we don't need to recompile all the binary. So these two diagrams shows how SVE defines the vector registers. So in the left, this is we can see that it has some bottom. The bottom 128 bits were shared with ARC64, SIMD, and FP registers. On the right-hand side, there's an example of a 256-bit implementation of vector. So we can it can be viewed as two Q 128-bit elements, and also the four double word elements, and as well as other 16 8-bit elements. Sorry.
You also have, in addition to the traditional D's and Q names, you also have the Z name. Can you use the Z name in any instructions, like Z?
Yeah, this is the instruction prefix. So you can treat the register as the D elements or Q elements.
No, but what about the Z elements? Can you refer to the Z elements of a vector register? Because you have the ZEN thing. Can you talk about ZN operands?
This is sorry.
The Z version, like you have the Q names, you have the Z names, can be used as well?
No, you cannot use that. No. So this is the per-lane prediction. SVE has 16 scalable predicate registers, P0 to P15. 1 bit of predicate register is mapped to 1 byte of vector registers. The predicate register is this means that a predicate register is 1/8 of the size of vector register. And a predicate register is also the implementation defined multiple of 16 bits. among these registers, P0 to P7 is the governing predicate, which means that this register can be used in the instruction to use as a line mask to determine the active elements. And also the predication supports zeroing and merging operation to the inactive vector elements. This is an example. This is an example of the of how SVE defines the predicate register of 256 implementation. So if we treat the register the Z register as an element of word, so the P register will have this kind of view. So in this example, if the lowest bit is 1, and then this element will be active. And if this is 0, and then this will be inactive. Inactive means that in your operation or your instructions, this element will not be included. And if we treat the same P register, but we treat the Z register as the double word, then these are we only take these bits. So all these elements will be active. So let's check. We have talked about the we're talking about the VRA programming mode. So VRA programming mode is very important to SVE. So SVE implementation, you know, as we know, that may have different actual vectors lines. VRA and SVE allow the same program to binary to run around to any implementations. VRA is also made possible by the plan prediction and the predicate-driven loop control, vector partitioning, and software management speculation features of the SVE. I will have an example to show how SVE and VRA work. So this is an example. A typical C function will look like this. If the compiler will usually have auto-vectorization ability, will generate the code like this. So this is the main loop. We will generate neon instructions to do the main calculation of array add, the vector add, and then we still have a tail loop which handles the unaligned the remaining elements. So the tail loop is quite long. So for the SVE, the code size looks much smaller. I will go through the assembly code to. First, we just need to set the scalar induction variable, which is I. We just i's initial value is 0, and then we will set up the entry prediction, which we compare the array length to the 0, and if the array length is larger than the 0, we will set the we will have the corresponding elements in P will be set. So based on the predicate setup, we will load data from the two arrays with the same predicate registers, and then we will have we will add this register and then store the result to the target array based on the same P register. And we will increment the induction variable by vector element count. If, for example, if we have an implementation of 256, so this x4 will be increased by a, which means a word. So at this point, we programmer don't need to know the real vector length, the real vector implementation register length. So after that, we will generate a predication for the next iteration. We will compare the induction variable x4 to the array length, and with the comparison, we will set the predicate register P0. If for example, if there's some element, for example, if there's 4 elements left in the final loop, we will only set four bits in the P register with the corresponding elements. So then we will base on the if there's any active elements, we will loop back to have next iteration. So we can see that there's no tail loop. So this is because all the tail loop has been handled by the prediction. So then I will talk about the SVE enablement in OpenJDK. We can obviously see that in OpenJDK hotspot there will be some work. For example, the assembler, the intrinsic, and C2 compiler. And in C2 compiler, we will have register allocator, which will need to support the scalable vector size and also the predicate registers. And also we will need to have backend code gen, which will to generate SVE instructions. And we will probably need a new vectorizer to support VRA programming mode. Since currently the OpenJDK C2 compiler auto-vectorization does not work, does not quite fit for the SVE, so we will probably need a new auto-vectorizer. This is hotspot VM, but what about the API call libs level? So as some of you may know that Oracle and Intel has a JP 338. They present a new, they will propose a new vector API. Is the vector API friendly to SVE? I think there's still a lot of some work to do to make it to fit for the SVE, so it still have to be improved. But can SVE help for the? But can Vector API help for our SVE backend enablement work? I think my answer is yes. If we have enabled Vector API backend, we can easily verify the backend code using the Vector API. So what is Vector API? So in JP 338, Oracle and Intel proposed an initial iteration of an incubator model, which is jdk.incubator.vector. It is to express vector computation, which can make hardware to use to make as much possible as its SIMD ability. So it will try to make use of the CPU's SIMD ability by using pure Java code. And it will also export data parallel operations through a set of cross-platform APIs. With the well-defined Vector API, we can easily map high-level Java API to low-level SIMD instructions. Currently, the Vector API is developed by Oracle and Intel. I will have an example to show how vector API work. So this is an example. It is just somewhat like neon C intrinsic. So first, we just need to create a new object with this is an example with fixed vector lines. We just need to new a shape with a fixed line, right? For example, this is 128 bits, and then we will load data to the vector registers. Use the predefined API, and then based on the created object and the data, we will add the value, and then we will store the value back to another array. Unfortunately, we still need the tail loop because we don't know that whether this array can fit the vector correctly. So we have another version which use you can see like this. We have to we write code hard code with 128 bits, but if we run this code to other hardware, the performance will not good. So there's a new more portable version. That is, we just need to create a template Java code, and then we use an API to get a preferred species, which in this API we will query the hardware resource and get the preferred vector size, and then we based on the space vector shapes, we will add the vector, and then yeah, just like above. Okay, how does it work from Java to machine code? This is an x86 example. I got this slide from Vladimir, the Oracle engineer. So for the high-level Java code, this will be intrinsified to the low-level hotspot C2 compiler IR. With this low-level C2 compiler IR, we can easily generate the machine code by this. Okay, so how currently Vector API supports Intel BIOS 64 bits to 128 bits to 512 bits. This is their vector shapes. The current vector shapes map to Intel's architecture and Intel's AVX, for example, XSMN, YMX, SAML directory. But how can we use this to map to our SVE? Do we need to implement all those SVE supported vectors? For example, do we need to add int 386? I think in our implementation, we just need to add a new scalable vectors, which will fit SVE quite well. With the scalable vector shapes, we can reuse current Oracle and Intel's work with current middle-end code easily. Actually, this is actually a known vector size represented as a scalable for SVE support length. So a scalable vector length, it can be any other SVE supported length. For example, the 2048 bit. So we just get the preferred vector length from the runtime. Use this API to get the getter length of the SV implementation. So this is how C2 compiler implements its vector nodes. So C2 compiler has a lot of vector nodes, which with a given type of length. So this is current type. The type has associated length. Currently, we have type vector S, D, X, Y, Z. S is a single word, D is the double word, and X, Y, Z maps to Intel's X, Y, and Z MMX directory. So, so to implement in hotspot C2 compiler for SVE, we just need to add a new vector type. What we add is vector type vector A, which means that it's a length agnostic type for SVE. So how do we define the vector registers? So currently we use the 8-bit mask to represent a scalable vector register, which is the double of neon bits. Since this 8-bit is not a real, the real 256 bits, it is actually SVE registers. We need to do some special handle in register allocator for these bits. This is how we define the register in the OpenJDK architecture description file. This we define a vector A reg set. And this is how current architecture description file generate the register mask. The A, D, and X. X is 128 bits, and D is the 64 bit, and A is just we just know we use A mask bits. Actually, the real size of vector A reg is actually known to the JIT compiler. So this is the code gen for the SVE. Currently, we only have unpredicate version for now. For predicate support, will also be added in. This is how we define the vector register, and this is the code gen code we use. We will require two vector registers and one for another one for destination, and then we will have the match and generate the code. So this is what our current work. We will for the future we will add predicate and mask support for the vector API, and this will include the generic mask computation. Current vector API have the masked API, so we need to support that, and we will need a better vector loop shape for SVE. You know that SVE will have the YVR18 programming mode, which we need to we will need to get the support in in vector API. So Oracle Vladimir have some initial thought on that, but there's no actual work. We will try to follow up that. And obviously, we will have octo vectorization support. And this is our current work. The current work is still in development, so it may be changed when upstreaming. Our initial patch has been signed out, which has the vector API support. Okay, thank you. Any questions? Hi.
Thank you. You mentioned intrinsics, adding support for intrinsics in the hotspot. How do you use intrinsics in Java?
In Java?
Yeah.
Sorry.
Is there some sort of API or?
For example, Yeah, this is kind of intrinsic. This is actually an intrinsic. Yeah, in API level, we will mark this as intrinsic, and then the hotspot VM will know that this function is intrinsic, though we will generate code based on the known function. Yeah.
Okay.
So we know this is behavior, so we will generate code for this API.
Okay.
Yeah.
I have another question. You mentioned auto-vectorization at the end. Is there already auto-vectorization for
No.
other architecture?
No.
Not for SV, but for like Intel, do they already support auto-vectorization?
In hotspot VM, we have auto-vectorization support in C2 compiler.
Okay, thanks.
So I was curious about the SVE support for the predication. So can you do something like one of the things I've been doing some work on is multi-precision arithmetic with vector instructions, and to do that you want to be able to say that I want to shift one vector, one lane at a time on every loop, and then I want to basically have the predicate also shift with it and say, you know, I want to do the multiply, accumulate, add, multiply, add, just for wherever I've shifted the one vector that I'm doing the multiply by. So I'm taking a scalar, logically a scalar of maybe 32 bits, and then, you know, maybe 16 things to be multiplied. I multiply the scalar by that thing, and by the whole vector, and then I add that vector to an accumulated register, but I keep wanting shifting it over. So that means you have to have a thing where when I say that I want to, this predicate register bit is 1, it means that I want to do the multiply for that lane and the addition, but I still want those other lanes in the accumulated register to still be preserved. I don't want the output to just be the output of the predicate register.
I don't know whether I understand your question. So you mean that we will try to use the predicate to the multiply add? Yeah,
and so when you do that, what happens to the lanes that do not have the predicate value of 0? Do they retain their old value when you do a multiply accumulate, or do they retain the old value? They don't, and then the predicate just determines who gets incremented, who gets the multiply increment change.
I see. Sorry. ATG architecture.
It depends. You can say 0 or merge. So that was on your slides earlier. So you can either have the predicate, or say, operate on these fields and 0 everything I don't operate, or operate on these fields and keep the result that was in the source on the fields that don't meet the.
So where do you specify which flavor you want?
Yeah, you can specify which flavor you want.
Where's that?
So on this LD1W, Z1.S, the line below the P0/Z. So the lanes the predicates I don't load, I'm zeroing in that example. I could have just had an M and that would have merged.
So it's when you set up the predicate register, you say what flavor the register is?
No, it's when you use the predicate.
Oh, you use it, okay.
Yep.
And can I shift the predicate register by one lane as well as the...
I'm just checking the instruction set.
Okay.
Give me a minute.
Yeah, we have to check the instruction. Okay. Any other questions? Okay, thank you.